Hollywood, and Newton's third law. Now, in this lecture, we want to look at collisions and the physics of collisions. But like many of Hollywood's offerings, they get their physics wrong. So today, I hope we can explain how a clip from a popular science fiction movie is flawed from a physics perspective. So let's review. Newton's third law says that for every action there's an equal and opposite reaction, or more physics, as an object is accelerated by a force and therefore increases its momentum, there will be an opposite force as well. So forces come in pairs. Force in one direction, force in another. The law of conservation, LOC, of momentum says that the momentum in the beginning must equal all the momentum in the end, and if I write that mathematically, it says momentum initial must equal momentum final. And so all the momentum to the left has to equal all the momentum to the right. And so if we start talking about net, that means that my net momentum must be 0 kilograms times meters per second. Okay, so let's play a game that some people play at camp called I Would Rather. In other words, you're given two very bad situations, and which one would you pick? So consider this situation. I have a baseball bat and I have a pillow of almost exactly the same mass and that I can accelerate to almost exactly the same velocity. And if that is the case, then you can see that I will have about the same momentum. About the same momentum at the end. My question becomes, the pillow actually has slightly larger momentum, it's slightly heavier, but which one would you want to be hit with? Now I'm pretty sure everybody's going to say the pillow, but in reality, do you still have to suffer the same momentum shift as with the baseball bat? Why do you want to be hit with the pillow? Now, it makes sense, you obviously want to be hit by the pillow, but explaining why can be difficult. And this really comes down to a question of what kind of collision we are talking about. Now, there's this idea of inelastic collisions. Now, you might have heard of the term elastic in like your clothing or rubber bands, but we're talking about elastic in the terms of physics. Now, inelastic means not elastic, and inelastic collisions deals with materials that absorb some of the force of the collision. In other words, we usually call them soft. So for example, a pillow. And if we start to look at this in the terms of momentum, we still need to suffer the same amount of momentum change, but we increase the amount of time in which you get to suffer this activity, or this momentum shift. So for example, if you get hit with a pillow, you have a very large amount of time in which to change the pillow's momentum. The flip side of that is an elastic collision. And this is a material that does not absorb much force of the collision. We usually refer to these things as hard, and think baseball bat. Another way of thinking about it is it returns most of the momentum. It doesn't absorb any of the force, and so all the force that the baseball bat applies to you, you have to accept. Also, it does it over a very short amount of time. And so therefore, time is very low, and you have to accept a lot of force. The movie that I'm interested in is called Minority Report, and in one segment of the movie, our hero gets his hands on a pretty cool weapon. Okay? He picks up a sonic weapon, which uses sound in order to shoot the baddie. But there's something strange about this movie. Okay, the baddie runs into a hallway, and suddenly his weapon slides out on the ground. And our hero runs out and grabs the weapon. And he proceeds to shoot the bad guy. Now, This film clip is really analyzing how the weapon is charged, but I'm more interested in right there. Do you notice what happened to the bad guy? What happens to the bad guy after he's shot? I'll show it again. Shoots another baddie, and right here, shoots a bad guy, and that bad guy is flung through all of these barrels. What's happening to our hero here? Why isn't he moving? And that is where the physics, and especially Newton's third law, falls down in Hollywood pictures. So of course we can take a look at this situation with free body diagrams. And so I have my hero here, and I have my baddie here. And my hero has a very large gun, a very large weapon. Are there any forces acting on both my hero and the baddie? Yeah, there's a force due to gravity. And since I know that Tom Cruise isn't falling towards the center of the earth, I know that the force normal is exactly the same, but in an opposite direction. And my baddie suffers force due to gravity and force normal. But in this situation, is my hero moving? Does he have a velocity? But he does have a mass. And my baddie, does he have a velocity? But he does have a mass, so we can talk about his momentum. In this case, the hero's momentum is 0, and he's not moving. And the baddie's momentum is 0, because he's not moving. But then, as the movie plays on, the hero shoots a projectile, in this case a ball of white light, at the baddie. And we know that that projectile has to have a lot of force behind it. And what happens to the baddie is he gets hit with it, and he changes his velocity from a very low velocity, 0, to some very large number, and he flies through a bunch of barrels. And so therefore his velocity is very high. But wait a minute. Do you see a problem here? I see that my hero's momentum is still exactly 0. Forces going to our right, but no forces going to our left, pushing the hero. Now, if I look at the way in which a bullet actually leaves a chamber, and this is a schematic of the way in which bullets enter chambers, I have the bullet and this cartridge here, and then the chamber in which the bullet fits. Now, when you pull the trigger, this firing pin starts a very large explosion. In the cartridge, which supplies an incredibly large force on the bullet and accelerates the bullet down the barrel. But Newton's third law says that there needs to be a force due to the explosion going backwards towards the shooter as well. This is called recoil, and every weapon that has a projectile on it will suffer recoil. But let's see what happens to a real weapon that is firing a very large, massive bullet. So what should have happened to the hero? Well, the hero in our movie should have suffered from recoil. And in this movie, he's firing a very large weapon called a 50 cal. And I want to watch very carefully what happens to the shooter. The very first thing that you see is that the shooter places this stock up against his shoulder, and that is really important. That allows the shooter to accept a lot of the recoil. Now you'll notice that he shifts his feet so that he has a very wide stance, and he kind of gets ready to accept a lot of force. Okay, now a lot of people focus on this part of the weapon, but what I want you, my physicists, is to watch what happens right here, along his shoulder. And I hope that you can see that his shoulder is being driven back. He has to accept all of this force. This is called recoil. There's a force being applied on the baddie, but there should be an equal and opposite force being applied on our hero. And he should be flying back into barrels. Now, Hollywood doesn't do this very often because it doesn't help the story. Our heroes look like superheroes and not confined by the laws of physics. It doesn't look cool, but boy, that bad guy flying through the barrels, that looks oh so cool.